Welcome to a reading from The Lucasian Legacy, the Lucasian Professorship of Mathematics at Cambridge University, 1663 to 1993, by Robert Bruen, as read by his son, Garth Bruen. George Gabriel Stokes, 1849 to 1903. He had the true spirit of a philosopher, more anxious to see science advance than he should have priority in advancement. Alexander McFarland. George Gabriel Stokes, 1819 to 1903, born in Ireland, followed Joshua King in the Lucasian chair. Stokes restored the dignity and integrity of the chair to the level of its first two predecessors, Barrow and Newton. Although great men such as Sir George Airy and Charles Babbage held the chair in the first part of the century, Airy held it only for 2 years, and Babbage, for all of his achievements, neither resided at Cambridge nor delivered any lectures. Stokes held the chair for 54 years, longer than any other scholar. Stokes came to Cambridge for his undergraduate years in 1837, the year that Queen Victoria took the throne and never left. Although proficient in several fields, Stokes elected to lecture on optics while holding the Lucasian chair. Stokes' basic field was physics, but his most important contribution was in fluid mechanics when, in 1845, he described the motion of viscous fluids. These equations are known today as the Navier-Stokes equations and are considered fundamental equations. Stokes independently discovered the equations 20 years after Claude Navier had arrived at them, but Stokes used continuous flow, not molecular flow, as did Navier, so the credit for the fundamental method is shared. As described by his contemporary, Stokes was modest, dedicated, hard-working, and religious. Administrative work and teaching slowed his productivity, but he pursued these activities out of a sense of duty. The Royal Society of London benefited from many years of his service as secretary, 1854 to 1885, and president 1885 to 1890. He guided the publication of their journals, Transactions and Proceedings, with a skilled hand. He was awarded the Rumford Medal in 1852 and their Copley Medal in 1893, and was president of the British Association for the Advancement of Science in 1869. Other awards included the Gauss Medal, 1877, the Arago, 1899, and the Helmholtz, 1901. The French made him a foreign associate of the French Institute, and the Germans made him a Knight of the Prussian Order of Pour le Mérite. An active member of the Cambridge Philosophical Society, he was its president from 1869 to 1902. He was also a member of Parliament representing the university from 1887 to 1891. From 1888 to 1889, he was a Royal Commissioner for the Reform of the University of London. Stokes gave the Burnet Lectures in the winters of 1883, 1884, and 1885 in Aberdeen, Scotland, on the nature of light. In 1891 and 1893, delivered the Guildford Lectures at the University of Edinburgh, Scotland, on the topic of natural theology. As an undergraduate, Stokes attended Pembroke College, graduating in 1841 as senior wrangler and winner of the Smith's Prize. He was elected as a fellow the same year. He spent virtually his entire adult life at Cambridge, 66 years. He was elected Master of Pembroke College in 1902, the year before he died. His contribution to Cambridge was as great as his contribution to science. He raised the status of the Lucasian chair after his immediate predecessor had occupied it without producing any memorable achievements. Professor Stokes is regarded as the principal founder of the Cambridge School of Mathematical Physicists, one of the main glories of the British mathematicians of the 19th century. Certainly these men who followed Stokes as the Lucasian professors were of the highest caliber. Stokes was unselfish in his attitudes towards scientific development. The awards and honors so important to scientists are acquired through public acclaim of credit for discoveries. To share this may mean sharing the honors or missing out completely. However, Professor Stokes not only lectured to junior members of the university and advised the senior members in questions of applied mathematics, but he was also very helpful to scientists in general. It appears that all who benefited from the generosity of Stokes shared the honors with him. Stokes was an applied mathematician working in physics, in the tradition of the work that had been done by professors of the Lucasian chair before him. And like many of his predecessors, he branched out into other areas while continuing to develop his own specialty. He contributed in many scientific areas, but his best-known work was in fluid mechanics, also known as hydrodynamics or hydrokinetics, by virtue of the Navier-Stokes equations describing viscosity. He treated elasticity and wave motion in solids and fluids exhaustively. As a result, he made important contributions to mathematics as he developed techniques and tools to assist him in his work. In 1843, he published a paper which spelled out his theory of viscosity of fluids and the famous equations of its influence in fluid motion. A second paper, published in 1850, used the contents of an earlier paper to solve several non-trivial problems concerning oscillations of a globe and a cylinder in fluids and the motion of various fluid around these geometrical shapes. The solutions had immediate applications to the study of ocean waves and electrolysis, and long-term applications to the design of aircraft and automobiles. The 1850 paper also reported Stokes' law, describing the terminal velocity of objects falling through liquids. Other discoveries were named for him. For example, the Stokes theorem, 1854, reduced selected surface integrals to line integrals. The theorem relates a surface integral taken over a surface to a line integral taken around the boundary curve of the surface. It is a generalization of an earlier theorem known as Green's theorem. In 1847, Stokes figured out the uniform convergence of a series. Kelvin noted that Stokes had done such outstanding work in areas of light and optics that he could be considered a great based on this work alone. One of Stokes' major discoveries was fluorescence. Explained in his paper in 1852, Stokes published the dynamical theory of diffraction in 1849, supporting the wave theory of light. Stokes was a religious man. He delivered the Gifford Lecture series on natural theology and then published them. In his book, he details his views on God and his relationship to the world. He was conservative in his views, mirroring the existing religious establishment. He was president of the Victoria Institute, which had been founded in 1860 in response to the scientific involvement exemplified by Charles Darwin, Origin of Species. Furthermore, he was vice president of the Evangelical British and Foreign Bible Society and active in the Church Missionary Society. He was outspoken on religious issues, speaking often in public and writing extensively to the clergy. As Stokes was a man who thought deeply and analytically, it is not surprising that his views contained beliefs from opposing camps of thought. For example, although he was an establishment believer, he embraced ideas of the evangelical movement, known for emotional attachment to religion devoid of the sophisticated theological positions of high church Anglicanism. Several major issues occupied Stokes in his religious thinking. One that bothered him from childhood was the problem of eternal suffering. He believed that because of his propensity for mathematics at an early age, the thought of infinity had far more meaning to him than to other children. He was unable to accept that God would make children suffer forever. In his more developed arguments, he proposed that Christ died so that we would not be punished forever. The principle of conditional immortality was accepted by him and many others. Stokes proposed as well that man consisted of body, soul, and spirit, rather than the dual nature consisting of only body and soul. The dual nature of man was first put forth by Plato, not the Bible, according to Stokes, and he believed that the concept was propagated by theologians and philosophers who did not go back to the source. For Stokes, the spirit was the element that provided the life essence to the body, and it survived death. The difficulty for him was explaining the difference between spirit and soul, but he also believed that the source of this knowledge was revelation and not reason. A third part of this religious thought was directionalism, a concept he created to oppose materialism. A problem had arisen from the new theory of evolution. It seemed that non-thinking, non-living matter was bound to living matter by the laws of the conservation of energy. Everything was bound together so that every event had a cause and effect. There was no free will, and no need for God or moral behavior. Directionalism stated that life was not energy, but rather directed energy, so it was above the conservation of energy laws. These were furious debates at the time, providing a pivotal point in the history of the relationship of science and religion. Thank you for listening to this segment of the Lucasian Legacy, the Lucasian Professorship of Mathematics at Cambridge University by Robert Bruen. To learn more or support this podcast, go to lucasianchair.org or our Instagram account, Lucasian Legacy.